Hey folks, Federico here. In this video we are going to create the basket without the lid. Still have to put the lid on, but we're going to do that in the next video. In this video we're going to create this beauty, which is a mesh created using the model that we made in the previous video, and then putting it together with the JIT geometry objects. And the cool thing about JIT geometry is that it creates a single mesh out of the multiple objects put together with JIT.GEOM multiple. So it's very different from GGL multiple, where you don't really have an output mesh. We have an output mesh with JIT.GEOM multiple. We can transform it into simple vertex data that we can export as an STL object, for example. So that's awesome. And we're going to see how to do that in this video. It's not really complex. I have a list here of all the JIT.GEOM objects. We are not going to see a lot of them in this video because mostly they're very well explained into the help file, and I want to keep these videos focused on these using JIT.GEOM to 3D print stuff. So without any further ado, let's get right into it. So since this is a 3D graphic patch, we are going to need a JIT world object. I'm going to give it a name, and let's call it geom basket. And I'm going to give it full scale anti-aliasing, floating one, the usual stuff, default size, and enable it by default, right? And I'm going to take the enable attribute here just so I can enable and disable the rendering. And let's now import the 3D model that we created in the previous tutorial. So let's use the GGL model for that, which renders to geom basket. Going to use the normalize attribute on it. So the size of the 3D model are going to be normalized, which means the maximum distance of its vertices from the center of the world is going to be 1. I think this means that. That's basically it. Oh, the file name. So we can either import a file with the read attribute. I call the file wallpiece.stl. So that should be it, right? And it loaded the model. Let's create a GGL camera so we can navigate the scene, and I'm just going to import it as a snippet instead of creating it from scratch. So I encourage you to save that as a snippet as well. I'm just going to change the draw to attribute to geom basket, and now I can move around with the keyboard keys WASD, Q, and Z in the scene. And let's just attach GGL material to that, just so we can get a better understanding of how this looks like. And this looks like this, exactly as the piece we exported in the previous video. It's going to look better when we piece a bunch of these together. So let's delete the GGL material, because what we're going to do is that we are going to output this matrix, so this shape. We're going to output it from GGL model, and actually just let's use the file attribute, so every time we recreate these object is going to load the correct model. Since this patcher is in the same folder as the model, that's why it's finding it. And so I was saying matrix output 2, so we're going to output the model, and then we can visualize it, for example, with GGL mesh, draw more triangles, and there we go. Here is the model. So we are outputting the matrix output with the value 2, which means it's going to output the mesh after it's being transformed. So if we rotate it or scale it, the transformations are going to be applied to the output. So for example, if I say scale 0.5, it's being output already scaled. While if I will say matrix output 1, it doesn't matter if we scale it or not. This will just output the matrix without the transformations. While if we say matrix output 2, it's going to output with transformations. And I think we're going to do some transformations on this. So we want to have it already output with those transformations like scaling and rotation. Cool. You know what? Let's go 1 second into a JIT.GEOM help file, and doesn't matter really which one. Let's choose the impulse, for example. I'm gonna open the help file, and inside the help file there is this geom render sub patcher. I want to copy these 2 passes from there, and possibly also the lighting, but not really. I first just want to copy those passes. And then actually, let's go back to the help file. Inside this abstraction geom mesh, there is a nice GGL PBR, which I also would like to copy. And I'm going to paste it and attach it to this GGL mesh. And now we can delete this object. It was just to open the help file and get those objects passed inside my patcher. So as you can see, this material, this PBR GL physics-based rendering, uses these colors, which if we don't like, we can also change them. Like, for example, we could change a bit the matte emission. Instead of having this green, we could have it matte emission we want to keep low, so we could have it a bit more blue, or yeah, maybe something like that. Now we can change the matte diffuse as well to something else. Can play a bit around. We didn't really import the light from the help file, so maybe we want to do that as well. But first I want to transform change attributes as arguments, so the new color that I've set here is going to stay hard-coded in the object. So maybe let's go back to JIT.GEOM dimples, and let's open the help file again with the option clicking on the object. I'm going to go back into render, and I'm actually going to copy that directional light because maybe it looks pretty good. And yeah, there's a lot of light now. So let's keep that here. Just some aesthetic stuff. This we didn't really do anything yet. Just some cosmetic things. Cool. So just to mention it, those two passes get automatically applied to the scene because they draw to geom basket automatically. If we check the draw to attribute is set to geom basket, and those are applied in cascade. So this gets applied, and then the big net effect gets applied. So these automatically draw to the scene. That's why you're not seeing any cables. This is applied at the final rendering step of the scene. So cool. Let's now start to work with JIT.GEOM. So the first thing we want to do, it is to, well, get rid of that cable and say JIT.GEOM to geom. So we're going to transform this matrix into the geom realm. First though, I'm thinking we don't really need the color information, the normals information from this object. These normals we're going to calculate automatically later on, and we don't really need texture coordinates. So what we're going to do is I'm going to unpack just the first three planes of this matrix with JIT unpack one output jump 3. This is going to unpack just the three. Just the vertex coordinates of the model. So we are skipping texture coordinates, color, and normals, all this stuff. We're just getting vertex coordinates, which is all we need. And then let's create a JIT.GEOM multiple. So JIT.GEOM multiple is very similar to JIT.GL multiple. The only difference, as we already said, is that combines all the meshes that it multiplies into a single mesh that it sends out then in its output, and then we can transform it into a GGL mesh data input, for example. So the first input of JIT.GEOM multiple accepts the geometry to be multiplied, which is our 3D model here, this bad boy. The second input wants the position where we should place all the copy in the space, and through that, so we want to have a basket, right? So what's the closest geometry shape that looks like a basket? I will say it's a cylinder with an open-ended. So what we could do is to use JIT.GEOM shape. And if we open the help file of this object, we can see that there is actually a cylinder shape. It's a closed cylinder though. So we could use JIT.GEOM shape, but I think the best for us is going to use GGL grid shape and just use the shape open cylinder, just because it's an open cylinder. Is this how you write it? Yeah, yes it is. And again, we just want to get the vertex position out of that, like we had for our model. We don't really care about texture coordinates. So first we want to output the matrix, so the shape as a matrix into our JIT.GEOM multiple. And second, we don't care about texture coordinates or normals or color. So we're just going to use again JIT unpack, jump 3, And first, of course, we need to say matrix output 2. If we connect that now to our JGL mesh, we should see the cylinder appearing. I think the normals are wrong because we didn't say to JGL mesh that it should calculate the normals. Okay, so we got this matrix out. We want to now use this matrix for the position of where the model should be placed. So let's do that, and we cannot just connect it like this, right? Because this is a GEOM object, it only accepts GEOM input. So what we want to do is to use another JIT.GEOM to GEOM, and this one's matrix or points, and this is outputting type surface. So let's go point type matrix, doesn't matter, we could go type point, but let's go type matrix. And let's input that into the second inlet. It's doing some calculations. As you can see, JIT.GEOM objects, when they do calculations, they have these cool stripes that animate. So this is like working on stuff. At a certain point, it should be finished unless I somehow messed it up. So after we did that, we now want to convert this back to a mesh, which we can do with JIT.GEOM to mesh, and we connect this to the mesh. And let's see what we got. So I think this is not giving us the proper results because we didn't set any scale or any rotation. So that's what we're going to do, at least the scale. The rotation should not really matter, but maybe the scale is messing it up. So let's do that, and let's create the JIT matrix here, 3 plane, float 32, and since this shape is 20 by 20, let's create another matrix that is 20 by 20, which we're going to use the same dimension for the rotation, for the scale and the rotation then. Let's really just fill this matrix with a single value and then output. So set all to whatever value we want, and then let's bang this matrix out. Another thing we should do is to set automatic 0 here on the JGL model and as well on the grid shape. Otherwise, at each frame, they're outputting their mesh, and the JGL objects are going to do the calculations. So let's attach a bang here. We could actually use a load bang, which we will use for both these objects. So they are loaded into the JIT.GEOM at the start when the patch is first loaded. Let's get rid of these passes. Let's put them here on the right. And so let's just try to do this. Oh yeah, of course we now need to connect to transform this into a GEOM. Again, type points or matrix. Let's just make it matrix. And let's give it a go. Okay, you know what? Just setting the scale didn't work, but I deleted and recreated a JGL multiple, and now it's working. So let's reduce the scale to something like 0.2, and there we go. We got a cylinder made up of our bodies, the wall pieces. Let's make it a bit smaller, 0.15. There we go. Let's actually load mask that. Now I want to have those holes facing the side of the cylinder, not being like all not being aligned in this way. So what we need to do is to rotate this wall piece. Now we could do that using the rotation matrix here, the rotation input, but we could also just rotate this input shape, and then we will have it rotated from the start. So I guess we want to rotate it 0, 90, 0. So 0 on the x-axis, 90 on the y-axis, and there we go. There we go. Now it's rotated so that it faces the outside of the cylinder. And by the way, the cylinder itself is rotated in a wrong way. Like if we reset the camera, I want the cylinder to be vertical. So I don't want the opening to face us. So what we can do is to rotate that as well. And since we're using matrix output 2, it's going to output the matrix with the rotation applied. So rotate X, Y, Z. Want to rotate it on the x-axis now, so 90, 0, 0. Let's give it a go. There we go. It's rotated. It's now vertical. Now, a thing that I can see right away is that we got too many vertical pieces for the scale of the object. So if we will keep the scale as it is, we'll have too many vertical pieces. So either we make the vertical scale really high, or we diminish the number of pieces on the vertical axis. And we are going to do that, because otherwise it will be such a high cylinder, a high basket. We don't need that. So we want to set this. Default dimensions we said is 20 by 20. So we can try with like 20 by 10. Sorry, I always forget that my face is here on the right bottom corner of the screen. And so, yeah, sorry, I was covering the rendering window. So we have too many pieces if we leave the default dimension 20 by 20. So what we want to do is to reduce the number of vertical vertices, and the vertices on the vertical axis. And so we could try 10, and if we see this is still too much, we could either scale this cylinder so it's taller, and we can do that by using the scale attribute here on the grid shape and setting the vertical scale to 1.2, then bang. Oh, no, that's actually not the vertical scale, right? Because this was before it was horizontal. The cylinder was not vertical as it is, so the vertical axis now is actually the zeta axis. So 1.2 looks good, but it's still a bit too many pieces, so maybe let's try 9 and 1.2, and then bang. And this looks perfect to me. We got exactly the right amount of vertical pieces, so that it looks good enough. There's a good proportion of height and width and radius, basically. And also the vertical pieces fit perfectly, so without really any space, I think, right? So great. Let's go here and transform attributes to arguments. So we hard code the dimension and the scale, draw to whatever. Now, what we want to do is to rotate those pieces so that they face the outside of this cylinder, right? And in order to do that, we can use the rotation input here. Now, if we check the help file of the JIT.GEOM multiple, we can see that the way the rotation matrix works is that it wants 4 numbers. One is the angle, and the other 3 numbers define an axis around which the vertex should rotate. So this is like the rotate attribute of GGL grid shape. So GGL grid shape has a rotate x, y, z attribute, which is the one I use the most. And then it also has a rotate attribute, which defines an angle and the axis around which to rotate. So the JIT.GEOM uses that syntax. So what we need to do is to get a matrix with 4 planes. Let's do that. 20 by 20. Well, it's not really 20 by 20 anymore, right? Now it's 20 by 9. So what we could do is to either manually set the dimensions of those matrix, or we could grab the dimension of the cylinder. Basically, that would be the best option, probably. But for the moment, we will just going to hard code it manually. So we take this matrix, which is with 4 planes, and then we need to use an algorithm to rotate those objects so that they face the outside of the cylinder. So let's go into Paint and do some visual explanation. So this is our shape. We want to rotate this shape so that so let's say this is the cylinder, and let's take this is our shape. And at the moment, our shape is rotated like this. So what we want is to get this vector, that is the vector that we want to align our shape with. Then we want the vector that the shape is currently facing, basically. And we want to rotate that vector around that angle. And we want to rotate for that angle around another vector, which is perpendicular to those 2 vectors. So imagine that this vector goes vertically to these 2, right? So if we rotate this shape around this vector in that angle, call it alpha, then it's going to align the shape with this vector and it's going to face the outside of the cylinder. Great. So let's transform these steps into max code. So first we need this vector, the green one, which is the vector that we want to align our shape with. And that's basically the normal of the cylinder, right? Because the normal is this vector that is perpendicular to the surface of a 3D object. And so we can use exactly that vector. And in order to do that, we can use again the unpack. We can add another argument for jump. So jump 3 vertices and then jump again 3 vertices. So use 3 vertices and then use again 3 vertices. And then offset 0 for the first 3 and then offset 5 for the next 3. So we skip the first 3 vertices, which are planes, which are the vertex coordinates. Other 2 planes are the texture coordinates, and then we get the normals. And by the way, this is all in the max documentation. I will put a link in the description, but it's all there. And then just we need to add another output here with 2, so 2 outputs, and that's going to be our normals. The normals are just 3 planes, so they are going to fill the first 3 planes of this matrix. The 4th plane is just going to be the first plane copied over. And so let's create a JIT.GEOM here, and this is going to be the rotation. Let's input that here, and what we want to do is to first switch XYZ. This is our normal. This is the normal of each point. So this is the vector we want to rotate to match it. And then we want to define a vector that represents the vector in which our shape is facing. In our case, that will be this vector here, right? And we can just define it ourselves. And since our shape is by default like this, let's connect this mesh to the model. And right, our shape looks like this. So by default, is facing in the X direction. Right? So we want to say that the vector in which this shape is currently facing is 1, 0, 0. So it's facing the positive X direction. So this is the model facing vector. Right. Let's normalize that. We need to normalize those vectors so they have a unit length. And that's because otherwise all our calculations don't really work. And then we want to get the dot products between this vector and that vector. And this will give us the cosine of the angle between the 2 vectors. So this will give us the cosine of this blue thing here. Can I zoom in? So this will give us the cosine of that angle. And then, if we want to get the actual angle, we can use the cos, which will transform the cosine into the actual angle. So this is the angle between 2 vectors. So just to be extremely clear, that's this angle here. And then we just need to find this vertical vector around which to rotate the shape. So in order to do that, we just need to do the cross product between these 2 vectors here. Which will give us this perpendicular vector. So this is the back around which to rotate. And then that's it. Actually, we first need to multiply that by rad2deg because the geom object wants degrees and not radians for the rotation. And then we can concat this single number with this vector. And that, believe it or not, should be it. So let's just write that that is the angle in degrees. So let's close that. Let's transform this into a matrix again. And let's send this into the last input. Let's click here. Oh, that's wrong. That's wrong. I missed something. I was so sure this was going to work, but of course it doesn't. So let's go back inside here. What I missed is that I could have missed to normalize that vector. Let's see if that's actually the problem. That was probably part of the problem, but it's not the whole Oh, by the way, that says the wrong attribute here. It's called draw mode. It's actually draw mode. That's nothing to do with our problem, of course, but... And I think that's because I rotated the mesh. So let's try to not rotate the mesh. So let's completely delete that. See if that works. And that works. So why is that the case? The normals should be rotated as well. But let's not complicate our life. This doesn't matter. We can just rotate the final mesh. So we can rotate that, rotate x 90, 0, 0. Exactly the same, kind of. So okay, this is looking good. I think the shadows are giving our shape a weird coloring, so I'm just going to take them out. Not super needed. Looking better. One thing I forgot to mention is that JIT.GEOM 2 mesh will actually also calculate the normals automatically. So that's also very nice. Now, if you notice something, and that took me a while to notice, but this shape, so there are actually 19 of these pieces that compose the cylinder. If you count them, you would see that they are 19, while the shape is actually 20. I should have 20 of those to compose the circle, which means that 2 of those are overlapping. And this is not a problem unless we want to 3D print the shape. And since we want, we cannot have them overlapping. So what we need to do is to get rid of one cell of this matrix. And we can do that by using JIT submatrix, for example. And say dim going to be 19 by 9. And of course, we have to change the dimensions of those as well. Yeah, an automatic way to get those dimensions will be better, but somehow I'm too lazy for that now. Cool, so now there are still the same amount of pieces, but not anymore overlapping. So we don't have this one row, this one column that is overlapping anymore. So that's good. Okay, cool. But as you can see, there are still spaces between those pieces. And so what we can do is to either reduce the radius of the shape, and I think this is the first thing we're going to do, or try to make these pieces bigger. So let's try to reduce the radius of that. So in order to reduce the radius, we can go here. I wonder... So there is not really a radius attribute, but I guess we could change the scale of the X and Y. Yeah, this will make it more compact. So let's actually create here a pack scale FF, or let's just say 0.9, 0.9, 1.2. Connect it here, and we're going to use a single number for the X and Y. And yeah, something like that. And I think we are getting there. This is actually starting to look pretty good. Maybe let's squash it together a bit more vertically. So 1.1. So that they are really connected together, and maybe it's 0.8 here. And yes, now they are pretty much connected together. I think they're overlapping a bit, which is not directly a problem, I think. But if we want to avoid that, we can... let's actually trigger the calculation in the geometry after we set the scale. So with a trigger, bang. List, these passes are always on my way. There's too few space in this patcher. Let's make these a bit bigger. Something like that. Yeah, something like this, I think it's good. And let's now change attribute to arguments. That's it. Cool. So we did it. We created our basket. Now it just needs a bottom, a lid or something to close it, which we're going to do in the next video. I think this video is long enough. I just want to show you that now we can export that as an STL. I just exported it in the folder. And now we can, for example, use Cura, the 3D soft 3D printing software, so to slice the meshes into instructions for the 3D printer. We can use this software to visualize this object and see if it will actually print. So if it doesn't print, it gives you like some warnings. So I'm opening that file. Takes a while because it's pretty huge. It's a lot of vertices. There we go. It's very small, it's tiny. So let's make it bigger. It's maybe like 60 millimeters. And I think it's good. There are not any weird surfaces. I think it's good. It's probably trying to tell me that I should use supports for these red areas, although that's probably not true. I think the problem is that the walls are too thin. Yeah, okay, there is a bunch of 3D printing things involved here, which we're going to see in the next video in the series. But this is already something. We could theoretically already 3D print that. So that's amazing. So yeah, this is it. I hope this was useful for getting familiar with JIT geometry. And yeah, we are going to explore more JIT geometry stuff. Anyway, yeah, thanks a lot for following. I will see you in the next video. This patch is available on my Patreon for all my subscribers. The videos, of course, here for free. And on Patreon, you can watch it free of ads. So that's also pretty nice. If you don't want to make a YouTube Premium subscription, you can subscribe to my Patreon and get all the videos ads-free. Anyway, thanks a lot. I will see you in the next video. Fun, take care, and see you soon. Ciao.